For those of you just joining, we are going to go ahead and get started now. All participants are muted, so if you have questions throughout this presentation, go ahead and type those into chat. We will open it up at the end of each section for questions, so make sure you get those questions into chat early. We will unmute everybody at the very end of the presentation, so if you have any additional questions, feel free to ask them then by either raising your hand or again typing those into chat. Without further ado, we'll go ahead and get started, and we'll start with a quick safety minute for just good measure, so everybody has that safety culture in mind. And we'll go with cold weather safety, since for most of us it is starting to get colder where we live. So just making sure if you are out in areas that experience freezing temperatures that you have the appropriate warm gear, whether that's wearing layers, gloves, making sure you have a hat on. And then if you live in an area with cold weather, making sure you have done your prep for winter weather and insulated your pipes or prepared your home to withstand that cold weather. And without further ado, Taylor, go ahead.
Cool. Well, thank you so much, Sarah. So to kick things off, I'll go ahead and do a quick introduction. My name is Taylor McClain. I'm the Director of Engineering for the Engineering and Interconnections Group here at GridSME. The Engineering and Interconnections Group is primarily focused on the preliminary stages of projects, from, hey, I have a piece of land, to can you prepare the technical package to get me a queue position. So what we're talking about today is really ingrained in the work that we do. We support a number of clients with a number of different types of resources, but as most can guess, inverter-based resources are a big part of what we do. And so what we're going to be going over today is going to be geared towards the inverter-based resource outline, but hopefully there's little nuggets throughout that kind of provide some insight into other types of resources, and we're kind of going to step through this from a very high level to towards the end getting into more of the power flow side of things and how everything relates to that. So hopefully there's some good information in here for everyone today, and with that we'll go ahead and get started. So here is the agenda that we're going to go. As I mentioned, we're going to start with discussing the major components that are critical to modeling and kind of step through them in a couple of different perspectives. And we'll kind of end things off by talking more focused on the power flow software side. This is the presentation is going to be made available afterwards, so this was just a bit of a helpful slide to have some lookups. You definitely don't have to remember all these. So with that, we'll go ahead and dig into the major components. So as we walk through the major components, I'm going to start on the BES side, which this is the bulk electric system, basically meaning the rest of the transmission system, all the electrical infrastructure. And we're basically just going to walk through this diagram all the way back to the generator. As I mentioned earlier, I have this focused on inverter-based resources. There are certainly differences in the components that are required and the layouts, but some of this stuff does still apply. But keep in mind that this is geared towards the inverter-based resources. So the first kind of part of the facility that we start discussing that separates from the transmission system or the distribution system to the actual generation facility is what we call the point of interconnection, and that is the point on the existing system where you plan to connect your generation facility and where your power will enter the system. And this point of interconnection, if you say you have a 100 megawatt project, that 100 megawatts is defined at the point of interconnection. So that means that this takes into account all of the losses and everything on your generating facility, and you end up with a 100 megawatts at the POI. And so from the POI, we then step back to the generation tie line, sometimes referred to as the interconnection tie line. But this is the piece of equipment that is going to connect the point of interconnection to your project substation. This is this is typically typically this component of the facility is aimed to be as small as possible to reduce costs and the right of ways that you might have to obtain to get to the POI. So, in some cases, depending on the generation type, you may see, 20-mile gen tie for geothermal is not entirely uncommon. But when you're looking at inverter-based resources, you're typically going to see this length under 10 miles, most often under 5, and certainly a goal to keep this as low as possible. If it can be under a mile, that's definitely preferred. In the previous slide, it mentions that a POI is either a substation or a line interconnection. Most often, we're seeing a line interconnection being proposed in order to reduce the length of the generation tie line. But in general, that is the piece of equipment that's going to take your power from your project substation and tie it into the grid. So the project substation is more of a term than a specific piece of equipment. The project substation, as shown here, is where you're going to see the main power transformers, the medium voltage connections, where all of your feeders come in, circuit breakers. You would typically have your reactive support devices located there as well on the medium voltage side, and your facility loads as well. One thing to note is that station service load is most always going to be fed from your project substation, from the medium voltage side of your main power transformer. But for inverter-based resources, auxiliary load is not always fed from the 34.5 kV bus. We won't get into that today, but just something to note that for certain designs, you may not see that at the project substation. And then just another item that we won't go into in depth today is the power plant controller, but that is an important part of an inverter-based resource facility. And just a note that typically the designs are set up so that the point of control for the PPC is at the high side of the project substation or the high side bus for the main power transformers. So inside the project substation, as mentioned in the previous slide, are the main power transformers. For inverter-based resources, you'll hear the main power transformer sometimes referred to as the main GSU or the power or primary step-up transformer. It kind of depends on which area of the country you're looking at. They kind of use different terminology for that, but it all refers to the same thing. And the reason that we have this differentiation, when you look at conventional gen, you may just see it referred to as the GSU, and that's because for conventional gen, that may be the only transformer at the facility. So it truly is the generator step-up transformer. For me personally, I think that main power transformer is the most clear, and I use that most of the time to refer to the transformer or transformers that are stepping up the voltage from the medium voltage to the high voltage at which the project is interconnecting at. So as mentioned earlier, facility loads are another component for inverter-based resources. I mean, for most generation facilities. For inverter-based resources, we're typically going to see two potential breakdowns for that load, and that's going to be your station service load, which is the substation lighting, controls, things like that. We typically see that be less than 100 kVA. So it's typically a pretty small amount of load. And then there's the auxiliary load, which is essentially anything that needs to be powered in order to generate power. And so those could be things for solar, like the trackers, or for battery energy storage, like HVAC. And so, as mentioned earlier, this can oftentimes be fed from the medium voltage bus of the project substation. Sometimes it has to be so that there can be separate metering and the controls there. But sometimes it is fed from the generator terminals. But at a high level, those are really the two types of loads that you're going to see for an inverter-based resource. So then the next part, and this is where we really start getting pretty specific to inverter-based resources, and this is the collector system. And, as you could imagine, for a conventional generation facility, there's, maybe 1, 2, 3 units. They're all located very close to each other. There's not much need to travel from the output of the generators a very far distance to the project substation. However, for inverter-based resources, using solar as a great example, the inverters could be spread out over hundreds of acres. And so in order to get the AC outputs of each of these inverters connected to the project substation on the medium voltage side, we need to have a system of either underground cables or overhead conductors, which can take that power at the medium voltage and interconnect it all at the project substation at the medium voltage level. And so later on in this presentation, we're going to talk about equivalent modeling. And so the collector system is one of those components, which for purposes of modeling, we do equivalent modeling. The next component is the pad-mounted transformer. And so this is typically located in the same exact location as the inverter, very often on the same exact skid. And oftentimes inverter manufacturers pair the transformer and the inverter as an option to purchase together. Going back to the discussions about the main power transformer and how sometimes those are referred to as GSUs for older conventional gen facilities. Technically, for the inverter-based resource, the pad-mounted transformer is the generator step-up transformer. We very often refer to it as the GSU. We also see it referred to as the inverter step-up or the ISU. But for us, most typically, we're calling it the GSU, or if we feel that that is going to cause, any miscommunications, pad-mounted transformer is always safe and to utilize, and typically people will know the terminology. So the pad-mounted transformer is there to take the inverter output, which is typically between 300 and 700 volts. That varies, but that tends to be the range. We're seeing most between 600 and 690 volts these days, but we see some down at 480. So the output voltage of the inverter comes in varying levels, but the levels are all too low to be efficiently taking that power and delivering it over the expanse of the collector system. In many cases for solar, we're talking about miles of underground cable or overhead conductor. And so if we were to do that at this lower voltage, there would be a lot more losses. The infrastructure would be a lot more difficult. So the pad-mounted transformers, for a number of other reasons as well, but for the main reason, step this up to a medium voltage level, which for most inverter-based resources is going to be 34.5 kV. These transformers step up that output to the 34.5 kV, where it can then run through the collector system and make it to the medium voltage bus of the project substation. And for the purposes of our modeling, once again, this is the pad-mounted transformer is another component that we use equivalent modeling for. So that will be discussed as well in the later sections. And then landing on the last major component of the the IBR generation facility is going to be your inverter or the generator, excuse me. This is basically just taking DC power of some sort, whether it's coming from battery modules, solar modules, and it is putting that into, making that into AC power. And as mentioned earlier, this output is, typically between 300 to 700 volts, and that is connected to the pad-mounted transformer. So one thing I haven't explicitly represented in here because it's not always included in an IBR generation facility is reactive power support. So I'll just put a small plug in for that can be a critical component of an IBR, but that really depends on the design that you're looking at, and which is why it was not explicitly covered today. So now we've kind of gone through from a single line diagram perspective, each of the major components, what they look like, and what function they play. So the next thing that I want to do before getting into how we take that and put it into a power flow model and the process of equivalent modeling is kind of take a look at this from the perspective of a geographical view of an existing solar facility. Um, in this case, I selected Gemini Solar. We went and toured their facility recently at RE Plus, and it was very impressive, very cool, and so it's fresh in my mind. But this can apply to essentially any solar facility. This just provides a nice example for this. So as discussed earlier, we have the POI, which is going to be, this location here. This is actually where it is physically interconnecting to the substation. This blue line marks the actual outline of the substation. And then from your point of interconnection, you can see that this green line running all the way over here is the generation tie line. And that feeds into the project substation, which is the yellow square here. And then I haven't gone and marked all of the collector systems and all of the inverters, but you can see very clearly where each of the inverters and pad mounted transformers would be located or is located throughout the rest of the facility. These are just marking the first couple here. So once again, POI, generation tie line to project substation. Within the project substation, we have the main power transformers, which you can see in the red squares there. From the main power transformers, we have the collector system, which I forgot to count ahead of this, but I think there's like 8 to 10, maybe more collectors coming out of here. And the collectors in this particular case are running in, stopping in at a pad mount and inverter location, connecting there, and continuing down the line. And as you can imagine, you could have a collector system that branches off and has multiple sections of the feeder. That's actually something I should mention as well, is the individual paths of the collector system are referred to as feeders. And these are typically aimed to stay below 50 MVA, sometimes a little bit bigger, but there will be multiple feeders to collect all of the generation output at the project substation. So that's the look of how things translate from paper to what they look like in the real world. And so the next thing to discuss now is the equivalent modeling component. And we're going to do this before showing you how, the SLD and the real world play into the model, because the equivalent modeling is very pertinent for the inverter-based resources. As you could imagine, if we had to explicitly model, every single inverter and collector system, there's a lot that could be involved. So here we're going to talk about the equivalent modeling and why we do it. So as I touched on a little bit earlier, there were 3 components in the discussion that need to be considered for equivalent modeling, and that's going to be your collector system, your pad-mounted transformers, and the inverters. And so, if we were to create a power flow model that had every single inverter modeled, we do some of these larger 500 plus megawatt facilities. Depending on if these are smaller inverters, you could be talking about hundreds of inverters that would have to be modeled. And so not only is this very time consuming, but then for the actual power flow to run and solve properly, as you can imagine, there are now a large number of additional branches and lines, additional transformers, and additional generators. So the equivalent modeling approach was developed to basically achieve very similar power flow results and cut down on the effort that it takes to model these things, and then further allow them to be modeled in a full system without taking up too much computing power. And so the equivalent modeling can only be applied to equipment with essentially the same exact specifications. We'll discuss that as we go through each inverter. And the equivalent modeling also has, things that show up, such as having different medium voltage buses on the MPTs. There are certain instances where you can't apply equivalent modeling to get to just a single inverter, a single transformer, and a single collector system. but in a lot of cases you can, and that cuts down on time and computing power. So moving over here, talking about equivalent modeling of the collector system. We do this for projects where we don't have a fully defined medium voltage cable schedule. But if you have ever seen a medium voltage cable schedule that comes with, 30, 60, 90 as-built single line diagrams, essentially you're taking all of that data as it relates to feeders, and you're considering every single run of cable, its length, its size, its ampacity, whether it's in parallel with another feeder, whether it's in series. And then you are considering the number of inverters that is behind any one of those segments of collector system. And essentially, you're creating a single line in your model that has resistance and an impedance and a susceptance value that equates to what it would look like if we were to model each of the generators and transformers and cable sections individually. So through this technique, mathematically proven, it is very close. If you actually take the step to explicitly model a full facility versus comparing it, the losses come out very, very similar. And so for the collector system, this is essentially taking what could be hundreds of lines and turning it into a single line for the purposes of modeling. And as we'll discuss a little bit later, there are instances where you couldn't combine every piece of a collector system. Some feeders may end up need to be separate, but ultimately the goal is to reduce the amount of equipment that needs to be modeled as much as possible due to just the size or the quantity of equipment in a full facility. So the next component is the pad-mounted transformer. And for doing an equivalent model of a pad mount transformer, you are going to, as mentioned earlier, you have to look at transformers that have the same specifications. So the key specifications to consider when looking at the pad-mounted transformers are going to be the MVA ratings, the voltage levels, the percent impedance, and the X/R ratio. If these items are varying, you can't combine them together to consider them as one component that can accurately provide the results that all of the transformers separately would. For the MVA ratings, you're actually going to just add the MVA ratings on top of each other. It is important to remember that as you add multiple transformers, let's say you had 10 pad mount transformers, they were all rated at 5 MVA, you are going to say that that transformer has a 50 MVA rating, and you also need to ensure to update the MVA base rating to be 50 instead of that 5 of just a single transformer. For voltage levels, percent impedance, X/R ratio, there are no changes that you have to do. They are left the same, and for that reason, you can't combine, transformers that have different characteristics or specifications such as this. So very similarly, moving on to the inverters, once again, when we're doing equivalent modeling, we're talking about combining the like for like inverters. Let's say you have SMA PV inverters and Tesla battery inverters. You're not going to be combining those two together in one equivalent model. You'll keep them separate for a number of reasons, and one of those that we won't touch on a ton today, but a little bit towards the end, is the dynamic modeling. Different generators have different dynamic models, and if you were to try and condense two separate inverter types into one single model, you would not be able to effectively capture the dynamic response of those two inverters properly. So you do have to keep in mind that you can only condense inverters as much as they are the same, and further, as much as they are behind the same transformers. So these things all have to be taken into consideration. But if you do, as an example, and we'll walk through this actually on the next slide, I think. As an example, if you were to have two main power transformers and they both have the same medium voltage bus, and you have one type of pad mounted transformer and one type of inverter, that is a design where you can effectively simplify everything down to just one single equivalent collector, one single equivalent pad-mounted transformer, and one single equivalent generator. Now, if we take that same example, but we look at it with separated medium voltage buses, you'll see that we then have to have two equivalent collectors, two equivalent pad mounts, and two equivalent generators. It doesn't matter that there is only one type of pad-mounted transformer, because we are not going to equivalently model the main power transformers and they are on separate medium voltage buses. We then have to end up with two of each of the equivalent components. And similarly, if we come down here, we only have one MPT in this example, so we know that there's only one MV bus, and all of the inverters connect to the same MV bus. But we have two types of pad-mounted transformers because this is a hybrid project with PV and BESS, and we have two types of inverters because of the PV and BESS. This would also result in two equivalent collectors, two equivalent pad mounts, and two equivalent generators. So there's a lot of different examples and possibilities for how this could turn out. There's even bigger projects where you're going to end up with, much more than two equivalents. But as you can imagine, it's still extremely helpful to be able to reduce the number of pieces of equipment that are being modeled, and the fact that the results are still coming out the same. This is the best way to tackle modeling these big facilities. So we've gone through how everything kind of looks coming from a single line diagram. We've gone through the geographical view of that, and we've talked about the equivalent modeling. So now what I want to do is kind of pull that all together and show you when somebody comes to us and says, hey, I want to build this 100 megawatt solar facility, how we then get that into the power flow model and what the PSLF EPC file looks like. Note now that there are other power flow softwares, PSSE, Power World. There are other file types. I am going to specifically use the PSLF EPC file here as the example, but after that we will talk about the other options where equivalent modeling can be used and the other power flow softwares where the syntax is going to be different, but the concepts and the overall data that goes in is really the same. So this is the EPC power flow model file that I'm going to use as an example for the rest of this. I kind of just geared this towards this presentation, but it came from a project that is a valid project. So, here you can see all of the bus data, branch data, transformer data, generator data. And as you can see, there's 17 PV inverters and 17 BESS inverters, but we do only have one PV pad mount and one BESS pad mount, and one PV generator and one BESS generator. And then up here, one PV collector and one BESS collector. So you can see that the equivalent modeling approach has been utilized here. So starting from the top down, first thing first is the bus data. So these are what the buses would look like on a single line diagram, a simplified single line diagram. And you can see that they all relate to their own line in the EPC file. We have the POI, the high voltage side of the main power transformer, the medium voltage side of the main power transformer, the medium voltage PV bus or the medium voltage pad mount, and here for the medium voltage for the BESS, similarly the low voltage for the PV and BESS as well. And so these are defined as buses, and then these all get connected by different component types. So the next we'll talk about the branches as they're called in PSLF. They're referred to as branches. These are the lines. This specifically here is the generation tie line. We can see that that's shown here as running from the POI to the high voltage side of the main power transformer. We have the impedance values and the ratings and a lot of other data as well that is a little bit less important and we won't be going into today. But looking here, we have the PV collector, the BESS collector. Down here, we have the PV collector and the BESS collector. Moving on to the next component, the main power transformer. In this example, there is only one main power transformer. It was not equivalenced. There is just only one. If this facility had, let's say, 4 main power transformers, you would see 4 of these records. If they had varying specifications, those could also be different, but we will not equivalence the main power transformers. In this particular example, this is just a 2-winding transformer here, and you'll see that we have an MVA base rating, impedance values for the transformer only for 2 of the windings, and then down here we have the PV pad mount and the BESS pad mount, found here and here. And as discussed earlier, these could be equivalenced. And so we see that even though there are 17 generators, 17 pad mounts, and a full collector system for both PV and BESS, we have effectively condensed that down to just a single transformer model, pad mount transformer model for each of the pad mounted transformers. And then that takes us to the generators section here, where once again, as discussed on the other components, we condensed 17 of these into their single model. I'm wishing now that I had represented what the individual rating of these were, but this value right here is the MVA rating for the PV, MVA rating for the BESS. If you were to divide this by 17, you would get the individual rating of each of those inverters in MVA. And then, the real power output, reactive power range, these type of values are similarly calculated by taking the individual output and multiplying them by the number of inverters that this single generator represents. And then here I've gone ahead because for the purposes of our standalone system modeling, we actually model the bulk electric system as its own swing bus generator. And so I've shown that here. We won't get into that topic very much. Certainly if it's something that folks have questions about and want to ask, we can get into it more. But you will see that there is a third generator here, but that is for lack of a better word, a fictitious generator, which is representing the rest of the system for the purposes of being able to test this model without on a faster time scale, really. So, I mean, and for other reasons, but we won't get into all of it. So the last component here is going to be the loads. We talked about these earlier. Nothing to talk about on the equivalent modeling side of these things. This is what they will typically look like. This particular project had a 30 megawatt battery. And so, we see the auxiliary load for those is oftentimes around 2.5 to 3%. As mentioned earlier, the station service load is, oftentimes under 100 kVA. Here we see it at exactly 100 kVA. So that's, another component of the facility as shown in the EPC file. And so with that, we've gone through now how this looks in the PSLF EPC file, but it's important to note that this is not the only equivalent modeling, and I mean modeling in general obviously is not specifically related to PSLF or the EPC file. You'll see here equivalent modeling is used for all of these types of modeling. You'll probably see, you'll hear of ETAP, which is another short circuit modeling tool. It does a number of things. You might see full system models where they've actually gone and modeled every single inverter, every single piece of collector system, every single pad mount transformer. But for the purposes of these interconnection request level submissions that we're doing, everything needs to be tested on a larger scale, on a full system scale. And so we see that, the equivalent modeling is used in all of these tools to aid in the ability of, accurately testing these without overdoing it on the equipment that's modeled. So shameless plug, at GridSme, we offer all of these services. So if you find yourself in the need of any modeling done in any of these services here or these tools, definitely reach out and let us know. So I touched on this a little bit earlier. everything that we discussed thus far was related to the steady state or the power flow model. This is looking at your, for simplified terms, your megawatts getting put on the system, and how that's what that looks like, what it takes to get your 100 megawatts at the POI, considering all the losses you have in your system. So this is the snapshot model. We'll say you essentially like freeze the system at one moment, and those were the megawatts and MVARs that were flowing on the system. That is your steady state or your power flow model. It is made up of, a number of other components, as well as all of those that we just went over for the generation facility. Now, on paired with this is done in, PSLF, PSSE, PSCAD. There are the transient, the dynamic simulations that are done along with the steady state models. The steady state models define the topology, and then we have the dynamic models, which define the characteristics of a generator. In this case, we're talking about a DYD file, which is specific to PSLF. DYD is the file extension. So if you see a .dyd file, that is a PSLF dynamic model. And this particular model here is for the BESS, and you'll see that we have the generator control, the electrical control, and the power plant controller here, as well as the inverter voltage and frequency trip settings. And so you assign, this model to a generator at a certain bus. And now when you pair this dynamic model with your steady state model that you've prepared, you can now see how your generator would respond to system disturbances such as faults. The most common that you're going to see is the POI fault done for new generator interconnection requests. Excuse me. And that is testing the dynamic response of the facility to a fault at the POI. So similarly, as I mentioned before, PSLF is not the only power flow software. This right here is a raw file. This is the PSSE version of the EPC, and it is also a .raw file extension, so that's how you'll know. As you can see, a lot of numbers, slightly different format, some different words and things showing up. Note that these are all commented out, so these actually aren't a part of the model. They're just helping whoever's reviewing understand where these numbers line up with. But it's all the same sort of information. You have, your POI, MPT, high voltage, medium voltage. This has 3 winding transformers, so there's tertiary buses, and your medium voltage and your low voltage. So regardless of what software you're working in, these types of files here define the steady state or the power flow portion. And on that same end, here is the dynamic model for PSSE, called a DYR because it is a DYR. Same components of the other: generation control, electrical control, power plant controller, and your voltage and frequency trip settings of the inverter. I will note, once again, this was geared towards inverter-based resources, so we haven't provided dynamic models or references for anything other than inverter-based resources. You will see differences in the types of models that are used and the layouts of everything. The parameters that are being required for other types of generation. But these 3 models right here, or similarities, you'll see, like this, for example, is for a BESS, it's the RECC. For solar is going to be REECA. REP-CA is for a single power plant or a single generator controlled by a power plant controller, and the REP-CB is for controlling multiple generators. So it's for inverter-based resources, it's pretty limited in what you're going to see on the WEC generic model side of things. For PSSE specifically, there are user-defined models, which also come in the flavor of a .dyr file extension, but these are models that have been prepared by the manufacturer and more accurately represent the characteristics of the inverter. In this case, you'll see we have a Sungrow UDM, and paired with a generic PPC model. And for the purposes of these types of models, for the generic model, these are all parameters that we can mess with, that we will mess with if we're not seeing proper responses. We need to tune it to a specific location in the system, or we're preparing models for a already operational facility. Whereas for these UDMs, there are some adjustments that can be made to frequency settings, voltages, some things like that. But for the most part, these are more of a black box type of thing. And the inverter manufacturers kind of have the insight as to, what parameters are actually set within the model that we can't access. And so these typically are going to model the responses better. They are a little less user friendly because you typically need support from the manufacturer, and they'll oftentimes require a library file, a .dll, which houses the additional characteristics of the inverter and the response that it's going to provide. So it can there's a mix between it requires more computing power and is a little bit more complicated, less easy to troubleshoot, but it does provide a better response, or a more accurate response to the inverter typically. So you'll see that for the most part, we're using generic models, but more and more we're seeing the requests for the UDMs. So these are both flavors of the PSSE dynamic model. And to kind of close that all up, this is your steady state model when it's all done. And this is a snapshot in time, as we had mentioned, or as I mentioned. These are the megawatts that flow if your inverter is outputting this, given these voltage conditions, this load, all of that. And this is just, a millisecond in time. And then your dynamic model, here you can see this is run from 0 to 40 seconds, and a fault was applied at 5 seconds. And so this gives you an indication of how your model, how your dynamic model reacts to a disturbance on the system. So with that, we are at the end. So I think I
We
have
got a
seen
couple
some
questions,
questions.
Taylor.
Okay, cool. Well, let's hope I'm ready.
All right. I will go ahead and unmute everybody, and then we'll start in the order questions came in. So Dimitri, I know you had a question. Would you like to unmute yourself and ask your question, or I'm more than happy to ask it as well? And I don't see you coming off mute, so I will go ahead and ask the question. So Taylor, what is the main objective behind performing the power flow or load flow studies for these facilities? And second part to that question, do you perform these studies after a facility is commissioned?
Yeah, so I mean, there's a number of different reasons. I mean, the very initial reason is, to be submitted with an interconnection request package. And the reason this is done is you can go to the utility and say, hey, I want to put 100 megawatts on POI X. Let's do it. They're like, okay, well, let's start having you prove to us that that you can actually get that 100 megawatts there. Because as we looked at from all the different components, you're going to be, to meet all the power factor requirements, to do all the things that it takes to have 100 megawatts at the POI and meet all the standards of the utility. You basically need to prove that that can be done with the equipment that you're specifying. So the power flow model, first and foremost, is a way to check that your design can get 100 megawatts at the POI, that your design can meet the reactive power requirements, that your dynamic model, which should represent how the inverter is actually going to function, can respond to system disturbances in a standalone system. And so that's kind of the initial reason for this. This then is taken once your package is accepted. Now they take your model and they put it in the full system model. Now they're going to test all of these things again, do the full system impact study, run contingencies on the system. And basically what you're doing by preparing these models and submitting them with your interconnection request package is you're indicating what your design is going to be, so that the utilities and ISOs can start looking at that design and saying, if you're putting an additional 100 megawatts on the system, are you causing overloads? If you put an IBR here, where the system is weak, if we experience faults, is that going to be a problem? Is your generation going to be tripping offline and then causing, additional problems further down the line? So there's so many different aspects to test from this, but the root of it all is that it reflects the design characteristics you have chosen for your project so that the ISO or PTO can effectively determine what those impacts are, whether it be with power flow, dynamic stability analysis, short circuit analysis, EMT modeling. It all is done so that they can say, hey, you're going to build your project in this way. We'll tell you what those impacts are. And then was there a second part of that question too? Did I get that?
The second part of the question, I think you may have answered, but do you perform these studies after a facility is commissioned?
Oh, yeah. So in different ways. So as you step through the interconnection request process, it's very, very likely that your design is going to change, even to the very end where you're going through the resource integration process and coming online, and there might even be some small changes. Your dynamic model might be based off of recommended parameters. So there are times, there's a whole subset of GridSME actually called the mod testing group, and there are different mod standards that have to be met. And these folks will record the data of the facility responding to real world events, to signals sent to the power plant controllers. And they will record the dynamic response of these units. And then they will go back, and this is all answering to the, after a facility is operational, they will then model this facility exactly as all the equipment is, find out what the dynamic model parameters should be, and then start comparing the power flow dynamic attributes to all the data, the SCADA data that was recorded during the testing. And they will start benchmarking those and tuning the dynamic model that they have until it matches what the facility is actually doing in real world. And so this is done consistently throughout the life cycle of a project to make sure that the dynamic models that the ISOs and PTOs have on hand are aligned with how the generators actually function.
Great, thanks, Taylor. All right, I see Terry has a couple questions, and Terry, if you would like to unmute and ask your questions, feel free.
Hi, Taylor. Great job on the presentation. Can you hear me?
Yep, I can hear you.
All right. I've noticed that some spot checks or align questions are asking where entities get their approved model lists. Do you guys have links to where we can find those? And
yeah,
if you
so
don't right now, that's okay.
Yeah, we can get that. So, I mean, WEC has an approved dynamic model list, and anybody in the WEC region is supposed to go off of that. I'm less familiar with, in general, I think the approved models in WEC are typically what flies in most other locations. To be honest, that's the reference I've used the most. As I'm answering this, I'm realizing there probably is some other resources out there. I think that if it were within their right, a specific ISO or PTO could, maybe, have their own personal preferences. But that WEC dynamic approved dynamic model list is really the best resource to go to for that. And so we can definitely get a link for that.
Thank you.
Yep.
Great. And then we do have a question from, I hope I pronounced it correctly, but Atir. And if you're still here and you'd like to ask it, feel free to unmute yourself. Otherwise, I'm happy to ask it as well. All right, I'm not seeing you come off mute, so I'll go ahead and ask it. What is the point during the interconnection process when dynamic studies are required by the utility or ISO?
So for that, I guess the terminology may differ on what stage it is, but really the very first study phase. So, the system impact study in a number of regions, or the phase one study, as soon as, let me say it better this way. So you have your cluster request window where you prepare your application, you submit it to the ISO or PTO, and they review for validness and completeness. And then the window closes. Now you have your customer engagement window, which is where they're going to dig into all the technical issues. You're going to have to cure your package, do all that. during this period of time, that's where you prepare and submit and update your dynamic model. And then as soon as the cluster engagement window closes and they start kicking off the studies, it's very likely that they're going to start with the steady state analysis first. But regardless of what it's called, the system impact study, the phase 1 study, during this initial study period is the first time that they're going to test your dynamic model. And so for your phase 1 or system impact study reports, you should get results that not only show what potential network upgrades you have due to voltage and thermal issues, but then also if there were any dynamic stability issues that were caused by your project and potential mitigations related to that. So very long-winded answer to say it is a part of the first study process that's performed, and it is continued to be performed for each phase of that same cluster study. Obviously, if this is a serial interconnection process, it's done slightly differently, but it's still going to be in that initial study phase.
Great, thanks, Taylor. And we have another question from Lither Shauna. Would you like to unmute and ask your question? And I'm not seeing you unmute, so I'll go ahead and ask it. How would the full system study work on the CAISO end if we have multiple sites applying for interconnection at the same time? Are they done in tranches?
Yeah, so I mean, using CAISO as an example, you know, well, with FERC Order 2023, most locations have their transmission level interconnections on a cluster study process. So, but using CAISO specifically as an example, Cluster 16 is opening in October. Every single project that gets submitted to Cluster 16 and gets accepted to be studied in Cluster 16 is all going to be studied at the same time. With more or less the same ranking because they're all considered in the same cluster. Cluster 15, which they are wrapping up the study results for now and starting to schedule scoping meetings. If you had a project in Cluster 15, it is going to be considered in some way for Cluster 16 if it is proceeding with the Cluster 15 studies. Essentially, let me say it this way, like projects that are in earlier clusters, if they continue to move through the generator interconnection process, their generation injection on the grid needs to keep being considered for future projects that come online. So, I mean, there are further breakdowns to be made between whether it's, you know, requesting full capacity or energy only or things like that. But to simplify things for this answer, you know, if you have projects in cluster 15, they are going to impact your cluster 16 projects. If you have multiple projects in cluster 16, cluster 15, whatever, any same cluster, they are going to be studied in tranches, but at the same time. So like if you have 2 projects in SCE, very likely, or I mean, you're not really going to see much of an impact on PG&E, you know, your projects in PG&E unless they're located right on the borders of those regions. But you know, if you have a project 16 or a cluster 16 project, that project is not going to negatively impact your cluster 15 project. So I feel like I just rambled and kind of butchered that a little bit, but essentially projects in the same cluster could play into impacting each other, especially if they're in the same location or in the same study area. Projects in later clusters will be impacted by, or could be impacted by projects in the clusters before them, but clusters before a later cluster will not be impacted by the generation in that later cluster. If that wasn't super clear, I'm happy to write it out at some point too, and maybe put a better answer together.
Great, thanks, Taylor. All right, we do have about 5 minutes left of our scheduled time. So if anyone has additional questions, feel free to type in chat or go ahead and unmute and go ahead and ask your question live. And if there are no additional questions, I did include a survey link for feedback on our webinars. We always appreciate the feedback so we can continue improving our webinars. And we do have a webinar scheduled for November, which will cover the mod testing, which Taylor mentioned a little bit earlier. And it looks like we do have one hand up. So go ahead and Michael McElhaney, go ahead.
Hey, Taylor, great job. Could you just talk a little bit about what you see coming in the future that are different in terms of potential modeling changes that are on the horizon?
Yeah, no, that's a great question. I mean, starting with the UDM, which I actually touched on a bit, that's something that we are seeing be required more. It used to be that, and we still do see this verbiage. There will sometimes be verbiage that says only submit a UDM if it's like more or less absolutely necessary, use generic whenever possible. But we've actually started to see requirements for submitting the generic and the UDM for PSSE involvement. So that's one change that we're seeing. But the bigger change that I'm seeing is that PSCAD is becoming extremely prevalent. It used to be very rare that we were getting requested to prepare PSCAD models for brand new interconnections. And now it's like maybe not 50%, but like we're getting close to 50% of some of the bigger ISOs, PTOs requiring these things at a much earlier stage. So I think that is actually one of the biggest changes that we're seeing, in not necessarily in the sense of how they're requiring to model it, but in the sense of what softwares they're wanting to do this in more often. I mean, ultimately, PSCAD takes a lot more computing power to run. Full system models is a totally different thing. To be able to do that, it makes a lot more sense to do it in these, PSLF, PSSE, Power World type softwares. But PSCAD does allow for more accurate modeling, especially when we're talking about the dynamics and things like that. So yeah, I would say that the shift is kind of more towards the use of PSCAD becoming more primary. And then within the models themselves, I mean, we are seeing some new dynamic models come out. I think the REAK-D has been out for a while. Like every once in a while, we're getting these updated models that are a little bit better. But for IBR generation, we've really worked out a lot of the kind of standards for how they are expected to be modeled. So over the past, 3 to 5 years, I haven't seen that much change in the request for how the models are being prepared. A little bit of refinement on our end. But I think to sum that all up, I would say keep your eyes on PSCAD. I think that's going to start to be more of a standard.
Excellent. Thanks, Taylor.
Yep.
All right, I am not seeing any additional questions, so we'll go ahead and wrap this up. For those of you who called in, we will go ahead and post this online on our YouTube. So if any of your colleagues weren't able to join, they can always watch this later. If there are any follow-up questions, feel free to reach out to myself or Taylor directly, and we're happy to answer any follow-up questions. So thanks a lot, everybody. Appreciate you joining.
Yep. Thank you all. Really appreciate it.
Thanks a lot, Taylor. Bye, everybody.